Hi. Now that we know how to define arbitrarily large infinite sets and how to compute on them, in the final segment of the lecture on induction and recursion, we shall look at how to prove properties over infinite sets. The problem is simple. Given an infinite set of elements, how do we show that all of them have a certain property, or that a given statement is true about all of them? Let us start with a really simple inductive proof. We start by defining the function sum on the positive natural numbers, such that sum n is the sum of the first n positive integers, 1 plus 2 plus, and so on until n. The hypothesis we want to prove is that for every n, sum n is n times n minus 1 over 2. An inductive proof of this kind starts with a basis. In this case, 1 seems a suitable place to start. We can just test the hypothesis for the value 1 by substituting it and calculating the result. It happens to work out in this case. And so the induction basis is proven. So now we know that sum of 1 is equal to 1 times 2 over 2. Now the induction step consists of showing an implication, an if-then statement, namely the implication that if the hypothesis were true for k, then it would be true for k plus 1. When our job is to prove an implication, we start by simply assuming the premise, also called induction hypothesis. We start to assume that the induction hypothesis is true. Then, with that assumption, we must show that the conclusion, also known as induction goal, logically follows. Let's do this for this example. Remember that we need to show the induction goal, which is an equality. The left-hand side of that equality is sum of k plus 1. And if we use the definition of the sum function, we can unpack this as the sum of sum n, sum k, and k plus 1. And that is where the induction hypothesis comes in. It gives us an alternative form for sum of k, which we can simply substitute into our equation. Then expand the k plus 1 to bring the fractions to a common denominator. And with a little factoring, we get the right-hand side of the induction goal, which therefore has been proven. Since basis and induction step have been proven, therefore so has the hypothesis, and the proof is done. And this is the general schema of a simple induction proof. To show the hypothesis, one needs to show the basis, and then the induction step from k to k plus 1. There are some pitfalls people using this kind of proof stumble over. These are some of those. Cumulative induction is another kind of induction proof that represents a slight generalization of simple induction. The generalization is in the induction hypothesis during the induction step. In simple induction, we assume the truth of the proposition only for the directly preceding value, whereas in cumulative induction, we assume it to be true for all smaller values. Suppose we have this function which computes the Fibonacci numbers. The hypothesis we like to prove is that g of n is always less than or equal to 2 to the n for all n. First, we knock down the base cases, 2 in this example. Again, we just calculate the terms by substituting 0 and 1 into them, which works out so the hypothesis is true for these two numbers. As before, the induction step is an implication, but this time, in order to show that the hypothesis is true for k, we assume it is for all m less than k. And this becomes our induction hypothesis, while this here is our induction goal. We start showing it as before by taking the left-hand side of the inequality and unpacking it using the definition of the function. We know k is greater than 1 since we have handled the other two cases already. K minus 1 and k minus 2 are both less than k, so we can use our induction hypothesis here and assume that the inequality holds for those two. This means that we can replace g of k minus 1 and g of k minus 2 with two terms that, per the induction hypothesis, we know to be greater than or equal to these two terms. So the sum also must be greater than or equal to the sum of g of k minus 1 and g of k minus 2. A little algebra gives us this form, which we know to be less than or equal to the right-hand side of the induction goal, which has thus been proven. And since the basis and step have been shown to be true, so has the hypothesis itself. And this here is the general structure of the cumulative induction proof. In principle, one can consider the basis to be included in the induction step. The basis is simply the part that does not need to make any assumptions about smaller values. It often makes sense to do what we did in the example by looking at the base cases separately, similar to what is done in simple induction. Now let us look at a situation where the set we want to prove things over doesn't consist of numbers at all, but is a set inductively constructed as a closure over a set of relations as discussed earlier. Such a proof is called a proof by structural induction. Take our little language as an example. We want to show that all elements of that language, all strings of that language, contain an equal number of opening and closing parentheses. Here, the basis is just the set that we started the inductive construction with. In the case of the little language, this was the set V of variable symbols. Every element of V contains an equal number of opening and closing parentheses, namely 0. So that means our basis is already proven. The induction step in structural induction also has the form of an implication, as before. More precisely, it consists of one implication for each rule or relation that was used to construct the set we are working on, in this case 3. The implication is this: if all input objects to a rule have the desired property, then so does its output object. In other words, the induction step consists of showing that all the relations used as rules or generators to inductively create the set preserve the property. The induction hypothesis then is that the input objects have the property, and we need to show that this implies that so does the output object, which is the induction goal. Let's see if we can convince ourselves such is the case for these rules. R1, the first rule, has one input object, some string s. Its output object is that string prefixed with a minus sign. So the number of parentheses isn't changed, and thus if the input object had a balanced number of opening and closing parentheses, so does its output object. The other two rules, R2 and R3, have two input objects, which they wrap in parentheses with an operator symbol between them. The sum of opening parentheses of the number of opening parentheses of the output object is the sum of the opening parentheses of the two input objects plus 1. And similarly for the closing parentheses. If their numbers were balanced in both input strings, they will therefore be balanced in the output string. This means the induction step's implications are true for every rule, which means the induction step is shown, and therefore so is the hypothesis. And this is the general structure of a structural induction proof. The most general form of induction abstracts entirely from the nature of the elements and only assumes that the set we want to prove some proposition over is well founded by some suitable order. If we have a situation like this, a well-founded induction proof consists of a simple implication. If we can show that for any element of the well-founded set, it has the property if all smaller elements have it, then we have shown that all elements of the set have that property. So the induction hypothesis is, given an element A, that all smaller elements have that property. And our induction goal is to show that therefore A does. The art in applying this technique is often, just as in the case of well-founded recursion, to identify a suitable order. However, if you do it, it can greatly simplify the proof when it has been found. To illustrate this, let us look at the hypothesis that every integer greater than or equal to 2 can be factored into primes. This is a proof on integers, so it might be tempting to try to use simple or cumulative induction here. Let's try well-founded induction instead. And use a strict version of divides as our order that establishes the well-founding. If you have doubts about it, convince yourself that this is, in fact, a strict partial order. Think about what chains look like in this order. That is, chains of inequalities, and what its minimal elements are. This is how one could picture a chain. The minimal elements of this order are the primes. Back to our proof. First, look at the cases where there are no smaller elements, that is, the minimal elements. As we saw, those are just the prime numbers, and every prime is trivially factored into primes, namely itself. Now the induction step. If n isn't minimal, it means some k not equal to n divides it. Which means for some m, k times m is our number n. Per our induction hypothesis, k and m can be factored into primes, and since n is their product, then so can n. By the way, how do we know that m can be factored into primes? Because by symmetry, m also divides n, and so is smaller than it.